live, and this automatically then it saves it as a YouTube video.
Mm-hmm.
Live, and this automatic. Okay. Good. All set. So first of all, thank you, Alex, for accepting the invitation. It's a pleasure to have you today for the QISS visual seminar. So we have Alex Kissinger that will give a seminar on extending the logic of influence and causation. And Alex, you can go.
Okay, hi, thanks. Thanks for inviting me to give a seminar here. I'm happy to be here and also to meet some of you all. So if you don't know me, I'm in some sense the new Bob as far as the Oxford site of QISS is concerned, and that I've taken over the kind of formal administrative role here. But I've also been thinking a lot about causality and related issues, so I'm very happy to be here and to be involved with this group. So I'm going to be talking about extending the logic of influence and causation, and I've put the extending in brackets, so I'm only really going to talk about that at the end. And I'm going to probably ask more questions than I answer in this talk, which is maybe a good thing. But we'll see. We'll see how that goes. So the context for this, or the goal, is to do what I like to call black box causal reasoning. So this is an idea that you have some agents or events or probes or some kind of named collection of things. And you really want to ask in quite an abstract way, can we model, observe, or prove properties about how these things are causally related to each other? Okay, so there's a couple of interesting settings to think about this. One is this kind of shared device setting. So you could imagine something like a Bell scenario where you have some agents maybe putting some inputs and then they're receiving some outputs. And you want to ask if there's some causal relationships or study things like locality and signaling. Another, and I think more interesting version of this or variation on this is a kind of shared environment situation. So here you can think about having some agents and they're in some local labs. So here we have, Alice, Bob, Charlie, Denise, and Evelyn or something. And they're in some labs and you don't know how they're related to each other. And their environment or their universe is the thing that's being put in the black box. So it kind of turns that shared device thing upside down. So for instance, I could have Alice before Bob, and what's secretly inside that box is some kind of wiring connecting this first process that Alice does to this second process that Bob does, and this composes the processes in this order. Or you could imagine the opposite order, or you could imagine things like having probabilistic mixtures of these causal orders, which capture some kind of uncertainty about the order these things are in. Or you could have genuine superpositions of causal orders, so things like the quantum switch, which probably people around here are fairly familiar with. Okay, and that last one is probably the most interesting, or at least the most strange, because it admits things like indefinite causal structures, which have been studied quite a lot lately. And I'm going to return to a couple of these examples of real or theoretical things which admit something like an indefinite causal order. So in particular, the quantum switch and the process matrices of the Vienna crew. Okay, so what's the setting? I said this is a very abstract thing. I've talked about black boxes. So what is a black box, and how do I model things that I can do to them? The setting is process theories. So if you know what these words mean, A process theory is a symmetric monoidal category with discarding. Okay, if you don't know what these words mean, then it doesn't matter, because I'm going to tell you what a process theory is. So it's a collection of boxes or processes, and these things can have one or more inputs and outputs. So if it has no inputs, I call this thing a state. You can think of this as the process of preparing a state. If it has no outputs, I call it an effect, which you can think of as like a predicate or a measurement outcome, something like that. And then rules for putting these things together in sequence and in parallel. Right, so here's a kind of a compose and a tensor. Identity processes, this is like the do nothing process, which is just a wire. This is the do nothing to nothing process, which is just some empty space and nothing happening to an empty universe. And we really want to allow these things to connect fairly arbitrarily. So we have things like crossing wires over each other. That's allowed as a process. And the interesting thing that lets you start to talk about some causal stuff is that you have this distinguished effect called discarding. Okay, and initially I'm not going to assume anything about discarding. It's just this thing that I call discarding. Okay, and the intuition is that some system is just being thrown away, or it's being ignored, or we don't have access to it anymore. Okay, so we don't make any assumptions about what this discarding thing is, but you can use it to start to make some definitions. And the most basic definition in this setting is called causality. So discarding enables us to say when a process is causal. And causality is really if I discard the output of a process, that's the same as discarding the input. Which you can think of intuitively, it's if the outputs of the process are ignored, then it doesn't matter which process I did. Okay, and a consequence of this is that the causal process only affects other processes which consume its outputs, i.e. those that lie in the causal future. Hang on, my dog has just gotten home. I'll be back in 1 minute. Hi, sorry. Working from home causes these things to happen. Yeah, so a consequence of this causality condition is that causal processes only affect other processes which lie in their causal future. Okay, so you can think of this as something like, there's no secret side channels inside of these processes. Really, everything about causality is captured by the wiring. Okay, so discarding also allows you to talk about signaling conditions. Okay, so you have to remember that I don't have any probabilities or anything like this around, but I can already, as soon as I have discarding, I can talk about things like no signaling. So first I'll say one-way signaling is where if I say I have a process on two systems, and if I discard, so you can think of this as Alice's input and output and Bob's input and output. One-way signaling says if I discard Bob's output, it sort of falls through to Bob's input. Okay, and you should think about this as saying that there's no way for Bob's input to influence Alice's output. Okay, so that's one-way signaling, or you could say one-way non-signaling. So Alice can send a message to Bob, but not vice versa. Non-signaling is, of course, then just the symmetrization of this idea. So here, this one says that Bob cannot send a message to Alice, and this one says that Alice cannot send a message to Bob. So together, this makes a non-signaling process. So this is really saying that Alice and Bob can't communicate. So this would be something that's suitable for, say, having space-like separated parties. Okay, so in the classical case, so here I'm thinking about classical probabilistic causal reasoning. Then My sort of ambient process theory is just matrices of positive real numbers. So that's what this mat R plus thing means. So it's a process theory whose objects are basically dimensions, so they're natural numbers. And morphisms or processes are matrices of positive numbers. Okay, then discarding is the column vector of all ones. And discarding a state means that if I sum it up, it sums up to 1. Oops, whoa, I went all the way to the end. Hang on. Not quite sure how I did that. Okay, so discarding a state says that its numbers sum to 1. So the causal states are probability distributions, and the causal processes are stochastic maps, so the things that preserve probability distributions. And then the signaling conditions are just the familiar signaling conditions, so these kinds of conditional independences on joint probabilities. Okay, the quantum case, we have a process theory which is called CPM, and this is the process theory whose objects or systems are Hilbert spaces and whose processes are completely positive maps. Then discarding is the trace. A state being causal just says that it's trace 1, so it's a density matrix. And then the causal processes are the trace preserving CP maps. Okay, so this is all very, very standard quantum theory. Really, and when you see a discarding, you can just think trace. Okay, so when things start to get a little bit out of the realm of standard quantum theory is when we talk about higher order structure. Okay, so how do we capture higher order structure? Well, I sort of grew up in Oxford, so my favorite way to talk about higher order structure is these things called compact closed categories. Okay, so what's a compact closed category? Well, it's a process theory, but it has built into it an isomorphism between processes and states, which sometimes we call map state duality. So this is really just that the processes from A to B are in bijective correspondence with the states on 2 systems. So states on a dual tensor B. Right, so in the quantum example that I talked about before, this is just the Choya-Minkowski isomorphism. But of course, you can do this in a perfectly classical way as well. And then rather than using a maximally entangled state here, I just use perfect correlations. Okay, so the way you define these things is for every system type, we say that there's a dual system and 2 processes, one which corresponds to a maximally entangled state, and one that is its sort of dual that satisfy these yanking laws. Okay, and what these yanking laws are really just doing for you is capturing the fact that this is indeed an isomorphism. Okay, so these are quite handy for working with higher order structure. The reason for that is now I can think of my system of maps. So I can think of all of my maps as a system itself. So this A dual tensor B system. So my supermaps are something which go from A dual tensor B, say like this, to C dual tensor D. Right, so I can write it as something that looks like that. And I can really write this thing, which is really something which takes processes to processes as itself a process. And what's nice is because these pictures are so flexible, we can start to use these kind of familiar comb-like notations, right? So this suggests that if I plug a box in here of something going from A to B, I'll get something going from C to D out. Okay, so this gives us a nice language for higher order processes. But it's kind of a blessing and a curse. And the reason for that is that if I think about duals in a compact closed category, so if I take the tensor of 2 things and I take its dual, well, that's the duals, the tensor of the duals. Okay, so the dual of the tensor is the tensor of the duals. Okay, that seems like a nice property. But then now if I think about this higher order thing, so here's something which takes a process from A to B and gives me a C out. Well, that should be interpreted as this kind of thing, okay, using this definition of my processes as states. But then if I work on this a bit, I'll see that that's just the same thing as this first order thing. Okay, so here I had a higher order thing, and here I have a first order thing. And they're the same in a compact closed category. Okay, so everything collapses to first order, which means that there's no genuine higher order stuff going on here. Okay, and that's a problem because when you think about higher order causal structures, preserving a causal process, which this is like being a two-comb, if you know this kind of terminology, that's different from just being a causal process. That's a stronger condition. So we really need genuine higher order structure. And here we don't have it. And the reason we don't is really this equation. So this kind of distributivity is the problem. So there's another thing which has been around for a long time, which is related to compact closed categories called star autonomous categories. And these things just get rid of this equation. Okay, so no longer is it the fact that if I take the dual of a tensor product, that it just turns into the tensor of the duals. And a consequence of this is that the tensor actually becomes two different tensors. Okay, so here's the normal tensor, which you're maybe used to as a physicist, but it also has a kind of De Morgan dual, which is often written as this kind of upside down ampersand symbol. Okay, so this symbol is called par. But you can kind of think of this as like this is like and this is like or, right? So I can see these things as kind of De Morgan duals of each other. So if I take not A and not B and I say not, well, that's A or B. Okay, so I'll come back to this kind of De Morgan duality in a little bit. Okay, so the recipe for getting a kind of nice theory which contains good higher order structures, which are really causally meaningful, is the following. So I start with a kind of raw materials category, which is compact closed, and it has a discarding. And I do something to it. So I start with this kind of raw material category C, and I do something to it to get this category cause of C. Now this thing is star autonomous, and the thing that lies inside of this category is a kind of logic of causation. Okay, and if I do this with matrices of positive numbers, I get higher order stochastic maps. And these things have actually been studied for a long time. They're called probabilistic coherent spaces. And if I do this for CPM, I get higher order quantum channels. And these contain things like two combs, in combs, process matrices, all of these kinds of higher order structures that are being discussed in the indefinite causal structure literature. But another kind of interesting thing is I can take some other C. So I can take just some weird C, which is not classical or quantum, and I can get non-standard causal models. So that's kind of an interesting thing to look at. Okay, so how do you do this? Okay, so here's a kind of summary of how I build this cause C thing. First, I'll tell you what the dual of a set of states is. Okay, so here I have all of the states of a system. And for some subset of all those states, its dual is just the set of all effects, which is normalized for all those states. Okay, so this is a way of just turning a set of states into a set of effects. If I take the dual of that, I get a set of states again. Okay, and then the set of states is closed So this makes a kind of closure operation, and the set of states is closed if taking the double dual gets me back where I started. Okay, so that's just something about sets of states and duals. What this cause-C thing is I take my types as pairs. So here's a system from C. So for instance, this could be a Hilbert space. Here's a set of states, which is closed. Okay, so this is a collection of states in that Hilbert space. And the processes should just be things which preserve that set. Okay, so for example, I could take the set of all trace one states, so the set of all density operators. Then the processes preserving that set are just the CPTPs, so the completely positive trace preserving maps. But I can take other sets and I get other interesting kind of higher order stuff. Okay, and interestingly, and where all the rich structure comes from in this new theory, is that I can also take duals of these systems. So if I take the dual of a system, I just take the dual of, say, its Hilbert space and the set of all effects associated to it. Okay, and that thing gives the thing a structure of a star autonomous category. Okay, so I'm just going to poke at this structure a little bit to maybe give some idea of what's going on here. And I'll talk a little bit about these two kinds of tensor products, so this tensor and par. Okay, so what's the tensor? The tensor is the smallest set of states, which is closed and contains all the product states. Okay, so I take all of the product states and I take its double dual to close it. The par is the biggest set, which is consistent with all of the product effects. Okay, so here I have an effect on my first system and an effect on my second system, and I take all the states which are normalized for all of those things. Okay, so if you're coming from, say, GPT land, generalized probabilistic theories, if you've heard of something called the minimal and the maximal tensor product, this is very much the same kind of idea going on here. It's just the only difference between those things and these things is here we're talking about normalization rather than positivity. Okay, so everything in sight is positive, but what's going on is I'm talking about whether things are normalized with respect to each other. Okay, and normalization really has a lot to do with this causal consistency. Okay, and then once I have these two things, I can define my space of maps as in terms of the par. So this is like the maps going from A to B is A dual par B. Okay, so that's the things which are normalized for taking a state on A and an effect on B. Okay, so whereas in a compact closed category, there's only really one interesting way to put two systems together. Here, there's three. Okay, so a question might be, you know, if there are interesting ways, so if I have this tensor and this par as two different ways to form a joint system, why might you have only ever heard of tensor? Okay, well, for first order systems, so these are systems of the form where I take all of my normalized states. Then the set of states in tensor is I take the product states and I take their double dual. So that's the dual of this effect, which is just all of the causal states, okay? So all of the normalized states. But then the par is this thing. So it's the set of all states which are normalized for these product effects. And again, that's just all causal states. Okay, so at the first order, the tensor and the par are the same thing, right? So that's maybe a good answer of, you know, why you never had to learn what a par was if you did physics in school. So why bother with these two things? Well, At higher order systems, tensor doesn't equal par. Okay, so if I start with first order systems, A prime, B prime, you can actually show that if I take, here's the space of all maps from A to A prime and the space of all maps from B to B prime. If I combine these with tensor, I get all of the non-signaling processes. Okay, so these are all the bipartite processes which are non-signaling from A to B or B to A. But then if I combine these things with par, I get all of the causal processes. Okay, so really you start to see a divergence between these two ways of putting systems together. Okay, and there's a natural embedding here. So if I have a non-signaling process, this is of course a process with no restrictions on it. And you can ask if there's other kinds of things in between. And it turns out that's also true. So the one-way signaling processes are things which look like this. So really there's two ways to think about a one-way signaling process, right? It's something where if I discard on the right, then it sort of falls through, or I can think of this thing as a two-comb. So here, if I discard later, then it falls through. Okay, so for a bipartite system like this, or a bipartite process like this, I get a kind of lattice of different kinds of conditions that I can put on this thing. Okay, so the minimal thing is non-signaling processes. The maximal thing is all processes. And in between, there's two ways in which it could be one-way signaling. Okay, and all of these things are embeddings. And if I dualize everything, well, it flips all the embeddings around. Okay, so if I take the duals everywhere, so now I have this kind of local labs picture where I have an Alice and a Bob here. Well, my minimal thing, which was my maximal thing before, is now just correlations. In between, I have these kinds of two combs where Alice is before Bob or Bob is before Alice. And then the biggest thing is I have process matrices. Okay, so these are not putting any kinds of restrictions on the causal order of this, just that it be consistent. So just that I get good probabilities coming out. And in fact, if you look at the kinds of higher order processes being studied in these papers, you'll always see that these things with indefinite causal structure contain a dual of this non-signaling processes. Okay, so they contain what's called negative occurrences of non-signaling processes. Okay, so yeah, that was a lot of kind of formalism in one go. So what's the point of this? What's the point of bringing in kind of this extra technicality? You know, why do we need two different connectives and all of this structure about duals and so on? Well, the place that this becomes important is when you start thinking about taking boxes with different kinds of causal structures. So say combs or process matrices, and putting them together. Okay, so at the first order, we have well-defined ways to compose and take tensors or we have well-defined ways to compose processes. Okay, and there's basically only two of them, right? If I have two processes, I can either put them in parallel or in sequence. Okay, and this kind of suffices to build everything. If we want to think about a kind of operational setting, these are the only ways that I can put processes together. For higher order processes, this is not so simple. So for one reason, taking the tensor product of a thing with a thing is typically not a thing again. What do I mean by thing? Well, think, you know, if I take a quantum channel and I take a tensor product with another quantum channel, I just get a bigger quantum channel, right? This is actually not the case for something like process matrices, which I'll talk a little bit more about. And also, there's just many ways to plug higher order processes together. And only some of these are going to be well defined. So only some of these will give you nice normalized probabilities, and others will give you nonsense. Okay, so we have to make sense of this somehow. And without some kind of formalism here, it just looks like a big mess, and you don't really know what to do. Okay, so how about this thing about process matrices that I said on the last slide? Okay, so something that you might think is true, which seems reasonable, is that if I had two process matrices, so now imagine that Alice and Bob sort of share process matrices as a resource, okay? And Alice shares, say, a qubit process matrix with Bob, and she also shares another qubit process matrix with Bob. Well, does that mean that she shares a 2-qubit process matrix with Bob? And it turns out the answer is no. And you can kind of see why this causes a problem. And the reason is that process matrices, well, they allow the causality to go in either direction. Okay, so if I had two of these things, it could be that one of them is witnessing the fact that Alice is before Bob. That's what this one does. And the other one is capturing the fact that Bob is before Alice. That's what this one does. And now, if it were the case that these things together were just a big process matrix, then I could plug in something like this, which basically gives me a grandfather paradox, okay? It gives me a time loop, right? I have this single wire going all the way around, and then I do a NOT gate on that wire, okay? So what's the value of that bit? It's nonsense, right? So this is an argument of why the tensor of two process matrices is not a process matrix. And this, therefore, is a composition which shouldn't be allowed, right? Because I can't treat this thing as a big process matrix, I shouldn't be able to plug these kinds of things into it. I get nonsense. Okay, so the question is, well, what is the tensor product of those two things? And what kind of composition is allowed? Well, in a compact closed category, anything goes. Okay, it's like the 60s. You know, you can plug things in however you like, and that's fine. That's allowed. So here I have something going from A to B, and then something back to B to A, and then I just plug the A back into A again, and that's fine. Okay, and that's something that we specifically want to rule out in this causal setting because it's nonsense. Okay, and star autonomous categories actually give us something that allow us to rule out these nonsensical situations. They come with something called an internal logic. Okay, so how does this work? Well, the types of this category have a logical reading. Okay, and I've already been using these kinds of logical words, but now I'm going to start using them a lot more. So I can read the tensor as and, I can read the par as or, I can read this kind of funny map, make a map symbol. This is sometimes called the lollipop. I can read that as implies. And I can read the star as not. Okay, so for example, this kind of definition of the lollipop now makes sense if I read this logically. Right, this is saying not A or B equals A implies B, right? Which, as you probably remember from school, is how implication can be defined. And here again is this De Morgan dual that I was talking about before. Not A or B is not A and not B. Okay, so this is the idea of this internal logic. So what's it for? Well, it's for this rule. Okay, so here's the kind of golden rule of star autonomous categories. A composition is only allowed if it corresponds to a tautology in the internal logic. Okay, so a composition is only allowed if it corresponds to a logical tautology. Okay, so let's come back to this loop. Okay, so this thing is trying to plug a psi of type A goes to B into a phi of type B goes to A. Okay, so is this allowed? Is this a tautology? Well, I can read this as a logical statement. A implies B or B implies A. Is that a tautology? Well, no. I mean, there can be some A and B which neither implies the other. Right? So this is not a tautology. So it's not allowed as a composition. Okay, now here's what you might think is kind of a related thing. Here I have a process being plugged into the dual of a process, which is a two-cone. Okay, now if I take the logical reading of that, well, that's A implies B or not A implies B. Is it a tautology? Yes. Yes. So that's a P or not P, right? And that's a tautology. This composition is allowed. So maybe a question you're asking now, or maybe not, it kind of depends on your background, is what kind of logic is this? You know, I mean, maybe your background is, well, logic is logic. There's only one logic, right? Or maybe you come from more of a tradition where you know that there's different kinds of logic which have different properties. And when I tell you something is a tautology, I really need to tell you what logic it is. Well, these things are things which are tautologies and just normal logic, right? The classical logic. But here's something which is a tautology in classical logic, right? A implies A and A. But in this internal logic, this is actually something which isn't true, right? And the reason that this is not true is basically because of no cloning, right? So if I have a state on a Hilbert space A, I can't use it twice. Okay, so that's the statement that this is not a tautology, right? I can't plug A into two places that want an A. Okay, so what is this logic? Well, it's called, here's the name for it, it's called multiplicative linear logic with mixing. Okay, so it's actually this tiny fragment of classical logic, which was invented in the 80s, really to handle a situation where you have resource sensitivity, okay, where you can't use things more than once. Okay, and I guess I've written this formal system mostly just to scare you. The way that you can really do proofs in this logic is with this kind of Ginson style proof calculus. Okay, so I can do these fully rigorous proofs in this logic by taking something that I want to prove and kind of chopping it up with these rules, and I get a proof tree which actually justifies a logical formula. Right, so this logic has been around since the 80s. And the reason I said that you know, just showing you the rules here was kind of to scare you is we've actually had automated tools for doing the hard stuff. So these things are called automated theorem provers for these logics. We've had these since the 90s. So tools where you can just type in such a formula and it will prove it for you. Okay, so now I thought this would be kind of fun. Let's just kind of hop in the time machine and go back to 1997. Let's just do that. Here's some notable moments from 1997. And let's see. Going back, let's make this maybe a little bigger. No. Okay, is this visible? Hang on. There we go. A little bigger. Is that visible?
Yes, we can see it.
You can see it.
Alex, may I
Yeah.
also just kindly remind you that we are at 40 minutes now.
Okay. How long is it?
Usually I mean, we're not strict. We ask for 30 minutes so that we have enough
Oh.
time to discuss.
Uh-huh.
There's no limit afterwards, but people tend to leave at some point, but it's up to you.
Oh, okay. Okay.
You can wrap up at your own time, and then everybody that's left, we can have a discussion.
Okay. Okay. Yeah. That's fine. Okay. Well, okay. We're at 40 minutes and we're in 1997. Right. So here's some notation in 1997. Okay. The tensor is the star, the par is the plus, implies is this arrow, and the dual is the tilde. Okay. And maybe I'll just kind of show you how this works. Okay. So we have four parties. So here's Alice, Bob, Charlie, and Denise. And now suppose Alice and Bob are in some possibly indefinite causal ordering. Okay, so here's Alice and Bob, and they have some causal ordering. So there's some special cases, right? So here's Alice before Bob. And one thing you could ask is it possible to prove that Alice before Bob is actually indeed a special case of just being in a general causal ordering? Well, as a logical formula, that looks like this. And now let's see if we can just prove that. And yes, we can. Even in 1997, there's a tool which I can just type this formula into, and then I get one of these proof trees. Okay, so now this is a totally formal proof that Alice before Bob is a special case of any causal order. Okay, and normally I'd step through this a little bit more leisurely, but maybe I'll just go to the big thing at the end, which is if I now have this kind of complicated arrangement. So here I have two process matrices, and I have a non-signaling channel connected between them. You might ask, what does this party A have with this party D? And the answer is that they only have an entangled state at most. They only have shared correlations. Okay, and this is actually a pretty non-trivial proof if you want to try to work this out by hand. But in fact, you can just ask a theorem prover in 1997. It thinks for a bit and it tells you, in fact, that that's the case, right? I mean, this kind of looks like gibberish if you're just looking at it for the first time. But here's all that stuff that I composed, written very formally in this logic, and here's the expression for just sharing an entangled state. And this is a proof that that is the same. Okay, so that was 1997. Maybe not the most momentous thing that happened in 1997, but something that did happen. May have been the last time that the UK won Eurovision. Anyway, so an open question is necessity. So proofs give a sufficient condition for when these causal orders plug together. Now, there are necessary and sufficient conditions for these classical and quantum cases. But the annoying thing is that they require solving linear constraints on huge spaces. So even when I have parties where everybody just has a qubit, the size of these spaces go something like 13 to the n. Okay, so as soon as I have something like 10 parties, I'm really into supercomputer territory to try to see if things are causally consistent. So if we could give a purely logical characterization for this could tell us something, well, on a foundational level, this could tell us something deep about causality, consistency, Coarse graining, so thinking about really lots and lots of things composed together. You know, can I coarse grain indefinite causal structures to get definite causal structures? So it could answer these foundational things. It could also be much more efficient. So typical proof checkers for these kinds of logics can actually work in linear time. So not kind of 13 to the n, we're talking about time n. So that could be a huge improvement, even practically speaking. Okay, so yeah, I was going to talk a little bit about some of these attacks on the problem and how it relates to other things people are working on in indefinite causal structures. But maybe I'll just jump to the jump to the big picture. Okay, so what's the goal here? The goal is a complete unified logic for causation. Okay, and that's the classical, the quantum, the generalized causation. And this could shed some light on some big questions, right? So what are most general notions of influence and consistency? Can insights from foundations be applied to practical problems? So for instance, you know, reducing this exponential thing to a linear thing is really solving a practical problem. And since this is the QISS, of course, you know, the big question, right? Is space-time a fundamental or emergent structure? You can really think about this in terms of consistency and composition. Okay, and I think these are all kind of great problems to attack with this kind of structure. And with that, yeah, there's some references and thanks. And sorry for going quite a bit over time, but yeah, thanks everyone.
Thank you very much, Alex. I must say that only 2 people abandoned the talk, so it seems going over time did not have any impact. People were interested. Yeah, I will just pass to questions directly. Is there anybody that would like to comment or make a question? You can raise your hand or just speak or write in the chat. Who is going to break the silence?
I had a question about star autonomous categories with density matrices. So I think I'm not too clear on that interaction, but I was interested in possibly applying that to researching conversational negation. And so wondering about the interaction of logical not and and or in a compositional framework with applying context. How would you, given a CPM-F help, how would you like raise that to a star autonomous category?
So you mean how do you go from, I see, so how do you go from CPM to a star autonomous category?
Yeah, that's my question. Thanks.
So the thing that gives you this extra structure is that now all of your systems carry around this extra information of your normalized states or what your good states are. So the first order systems carry around all of the normalized states, so all of the density matrices, for instance. Your second order systems could be, so an example of a second order system is something where you say, well, now my only normalized states are going to be things which correspond to a quantum channel. So like a trace preserving CP map, right? So it's really giving everything this extra data of what I'm deciding to call my normalized states of the system. That's what turns the thing into a star autonomous category.
A follow-up question: do you think this could work with normalization that's not trace normalization? So in quantum-inspired natural language processing or quantum natural language processing, in order for entailment between 2 different statements to hold, there's a partial ordering could be the learner ordering or some other ordering, Loeffner ordering, and that in John's paper from 2017, he investigated partial orderings on density matrices and found that normalization to largest eigenvalue less than or equal to 1 has nice properties for such a partial ordering, which is actually in domain theory a domain, but for trace normalization, all the partial orderings trivialize, and so there isn't any implication between statements. So, but a star autonomous category does have this notion of implication once again. So that's the confusion that I'm not sure about.
Right. So this implication is more like saying, you know, I have maps from this system to this system. It's different from the ordering, like a lower order ordering on your positive maps. It's more about what things plug into what other things, rather than trying to think of these things as logic themselves. Apologies for the dogs, but
so there is a question by DJ, I think, if you can unmute yourself.
Hi, thanks, Maris. This is Dean.
Dean, yeah, okay.
Hi, Alex. Thanks for the talk. I find it to be a very interesting topic. And I'd like to ask about one statement of yours, which is you said there are some processes that you can't compose, and it's nonsense to compose these. I find it a very interesting statement. I think I agree with this statement, but it seems there needs to be some qualification. Trying to find a short way to ask it, but so it seems the question is you can impose some rules on what you can compose and what you cannot compose. Maybe you can call these laws. And there's the question of the status of the laws. For example, to draw an analogy, there are natural laws, like laws of physics. But we also have laws that govern people's behavior, like traffic laws or civil laws. These are imposed by people, and these can be violated. For example, if the traffic law says I can't cross the street when there's a red light, I can violate it, but then the policeman would be happy and say you're doing some nonsense. So the question I have about your statement is what kind of law or rule are you thinking? Do you have in mind for the forbidding compositions? Is it a natural law, or is it something that's imposed on the way we reason about causality?
Well, I guess the best way to answer that question is I can tell you what the punishment is for breaking the laws, right? So the consequence for breaking the laws is that you get probabilities which add up to things different from one. So the point of all of these compositional laws is that your probability distributions sum to be one, which is a kind of a notion of consistency, right? So if you introduce these kinds of feedback loops which appear in certain types of paradoxes, usually this amounts to some event happening, some deterministic event happening with a probability that's either smaller than or bigger than one.
So I guess I take it as suggesting you think it's a natural law. I'm sorry, actually it's not clear. Because it's a consistency condition. That could be the consistency condition for our own ways of reasoning about nature, rather than say laws about say the standard model or a theory of quantum gravity. And I guess it's in principle possible you can come up with another framework to describe causalities that allows you to do composition, but still allow you to preserve the probabilities. Do you regard it as a possibility?
What was the last thing you said, sorry?
So now you're saying if I allow these compositions, the probabilities would not be normalized, or wouldn't sum up to 1. And that's given the condition that you're using the formalism you chose, which is you have a process theory and you impose the causality condition. So the question is it a law of nature to impose the causality condition? Can we have another formalism that works equally well without having to rule out these compositions?
Yeah, I guess I wouldn't see it so much as a law of nature as a law of as a kind of deductive law, right? So it's a kind of a consistency of probabilistic reasoning that you would want these things to add up this way. You can imagine theories which don't have this property. And I mean, in fact, another consistent theory is to just consider things where probabilities add up to less than 1. And that also works quite well and is quite useful for doing this kind of causal reasoning. But the thing you're reasoning about is not processes which happen. They're kind of things that could happen, like non-deterministic processes. So maybe a particular measurement outcome or something like that.
I guess maybe another possibility is to use some formalism like onions, which allows say renormalization. You don't impose the causality condition in one time direction or any time direction. You can define your normalization with respect to the operation you perform, and you always renormalize your probabilities. So that in the end, it's by assumption that everything adds up to 1 if you divide out by the common factor.
Yeah, which works unless your probability goes to 0. So this feedback loop where I have a naught in it, that actually happens with probability 0. So there's no somehow there's no way of getting out of that by renormalizing.
If I don't know if Anya is here and listening.
Yes, I'm here.
Yeah, I guess I vaguely remember you said something about 0 probabilities in your framework. I'm not sure.
But they are excluded, basically. They are impossible. So unlike this framework here, I suppose you don't allow the composition of arbitrary processes, so you declare this special null process that's just the impossible process. It's an extra ingredient. So I suppose that mathematically it just does not fit in one of those assumptions that underlie this framework that Aleks presented.
Yeah, I mean,
but I don't know which one precisely.
You can sort of add a, the universe explodes process to your, and then this.
Well, certain things never happen. And so they cannot happen. And that's an extra rule. We don't say that's probability 0, but it's another thing. It just doesn't happen. And for those things that can happen, we can write down probabilities, I guess, for outcomes and so forth. But maybe I just take the opportunity. I want to actually to ask you something related here. Don't want to take away the discussion from you and think, but maybe that's somehow related. It sounded to me to how Dean formulated his question. I was more about, again, it's about how you think about this rule. I mean, I've listened many times to the way you and Bob and others formulate this causality condition in your language. And I'm just thinking about, it is precisely that it's related to this question. Is it supposed to reflect some kind of a physical constraint that we could test? Or is it a definition for, we're going to call certain processes causal? Is there a way to, for instance, in your thinking, I mean, is there a way to test whether a given process is causal, for example, in practice? or I suppose this would depend also on how you define the tracing out condition, the discarding effects or the discarding operation. What does it, is there a way to identify in nature what that is? Or are we free to do it or just ignore something? And I wonder to which extent this mathematical formalism, where exactly it intersects with a potential falsification or verification or something like that.
Yeah. Yeah, I mean that's a good question. Like, so I think of discarding as more like a Rob Speckens uses this distinction of these kinds of causal and inferential ideas. So on the one hand, you have kind of physical stuff. So you have a kind of dynamics of whatever system you have. And you also have some kind of inferential layer, which is like how I'm reasoning about that stuff. And I see discarding as more like an inferential thing. It's more like a statement of I'm going to ignore these outputs, or you know, I'm choosing not to use these outputs anymore. And this causality equation is basically just saying that, you know, if you don't use the outputs, then it doesn't matter what process is being performed. I mean, whether this is something that's falsifiable is kind of hard to say, because I would say that there really are no non-causal processes, but you know, maybe this is an assumption that could somehow be tested.
Maybe.
Yeah, can I say? I find this confusing what you just say, that you think of discarding as inferential, in the sense that from the causality equation involving discarding, you actually you get this equivalence with physical causal structure, which is not inferential, which is very causal.
Yeah. Well, I mean, maybe it's just this idea of, you know, what does discarding mean? You know, it's I'm not really thinking, you know, I'm destroying the system utterly. It's more like I'm making the statement that I'm not going to use it anymore.
Bob, when you say, sorry to jump in, I'm also trying to understand something here. When you say you make contact with the usual causal structure, do you mean Minkowski spacetime? Light comes.
I mean, like, yeah, the causal layer underneath the fabric of spacetime. If you go into sort of axiomatization, first layer is causal structure, like Sorkin causal structure.
So there are subsystems that could not, in principle, have had any cause and effect relation between them because you're in space-like separation.
So there's a paper like by Aleks and then Matty Herbert and I, and then we show that having this principle is essentially equivalent to obeying causal structures, for process to obey a background causal structure. It's the same. So it makes it sort of very hard physically in a way. It's sort of it's a witness of the fact there is a causal structure that needs to be obeyed. It's hard to explain. It's just like with words, but there's a paper by Aleks and Matty Herbert and myself where we kind of show this correspondence between this causality equation and then this kind of respect for a physical causal background structure. But I mean, I agree. It in some way it feels very epistemological, like you ignore, but then you get all this hardwired causal structure from it.
And I mean, one thing is that these mathematics are very high level in a sense, so they can, you know, describe a lot of situations. But then you have physics. You probably have more mathematics than physics there, and I wouldn't say that they describe all physics because there's many physics that are beyond just quantum mechanics, probably some sort of extension. But I don't know if we can write QCD, for instance, with circuit diagrams. But you have this somehow, physical laws. So I've been trying to get my head around this. It's one thing to say, I assume there is no causal influence between some subsystems, which physically speaking can be a very good approximation in many situations. And it's another thing to not have it in principle, right? That's the difference between doing the Bell experiment in a room and going through all the trouble to do it in two separate corners of the world, so that there's not enough time in principle for this. And I'm wondering, is there a difference there? So these two situations, the Bell test, such that given the Minkowski space-time, there could not have been a causal influence between two subsystems at the time of measurement, and just doing it in a Bell room. Is this encoded anywhere, the difference between these two cases?
But it's kind of the same story as what you're saying. This background just say that for certain things, it is just impossible to have a causal structure. For others, it's optional. It's either impossible or optional. That's what you're saying.
Yeah.
Yes.
So the way I see this is, so in these process theories, we always draw these diagrams of some boxes, and they're connected by wires. And what's much more important in these diagrams is actually the absence of a wire rather than the presence of a wire. Because when the boxes in those diagrams are all completely unknown, so we don't know what these processes are, a wire not being there is really what you said. It's like that there's no possibility in principle of information traveling from one part of the diagram to the other. So really the right way to draw this kind of space-like separated Bell scenario is having some correlation with two wires out connecting to the two boxes, which are later. And the fact that there's no wires connecting Alice and Bob's box is saying that there's no way in principle for these to communicate with each other.
But if you do the Bell test in a room and you don't have this in principle guarantee, but in practice, because you wire things or whatever, you put the optical fibers, wouldn't you draw the same diagram? Or
well, no, then it's just well, it depends on whether you trust the agents to do what they say they're going to do. If you don't trust the agents, now it's just a box with two wires in and two wires out. There's no decomposition that lets you capture these missing wires anymore. It's kind of, you don't know anything if if Alice and Bob are now in a room. They can say they did a Bell test, but they could have done something totally differently. The way we would draw that is just as a box with two inputs and two outputs.
okay, so you are encoding space-like separation. You're saying that it's not an assumption about what the physics are. It's an in principle constraint. Okay.
Oh, you went muted halfway through.
Yeah, there are hand raised, so I will pass up to somebody else. Although I would be interested to continue the discussion at another point. There was Li Yao. I'm not sure if he's still here. Lia Ye.
Yeah, I had a quick question about if you have, so you mentioned if you take the tensor product of two processes, you can get something that's not a process. I think I can understand if you take a tensor product of two causal processes, you might end up with a causal process. But I don't understand what's the type if you take a tensor product of two processes, if it's not a process. What does that live in? And if you somehow take the star in this, take the logical not in the star autonomous category, how you can get a process again? I'm a bit unclear about that.
Okay, so the statement I made, and this was actually not my observation. It was from these papers. I think let me just not leave people out here. well, never mind. Anyway, yeah, here it is. It was first Gia and Sakarwade, and then Guerin, Crum, Bedroni, and Bruckner. But the statement is, if I take a tensor of two process matrices, so these are these things which have a possibly indefinite causal structure. You can imagine, you know, if Alice and Bob now, if you think of a process matrix as something that they can share like a resource, you might think, okay, well, they could have more than one of these things. So they could be in more than one, you know, shared causal structure, you know, whatever that means. And the question was, is the tensor product of two of these things the same as just having a bigger process matrix? And the answer to that is no. Precisely because you can see that you know, I can use this to create a time loop. So one of those matrices could be Alice before Bob, and one of them could be Bob before Alice, and then, you know, Alice can send messages to her own past. So you can actually see what the tensor of these two things is, because it is something, right? It's not a process matrix, but taking the tensor of these two things should give me some kind of map in this higher order category. And what the type of this thing is, well, it has a type which encodes exactly what you can do, exactly all of the consistent things I can do with a pair of process matrices. So for example, the kinds of things you can do is you can send sort of, Alice and Bob can both send information, say, to the left, or they can both send information to the right, and that's allowed. But Alice is not allowed to send information to the left while Bob sends information to the right. And actually, this internal logic will capture all of those kinds of constraints, which the tensor of these two things gives you.
Can I ask a clarification follow-up question?
Sure.
So you're saying that it's no longer the case that you can compose, say, like compose via composition of processes or tensor product, some processes to get some correct or causal process, but instead, whether or not that composition has a causal interpretation is determined by the logical rules of the internal to the star autonomous category. And so every time you write such a diagrammatic equality, you can then, based on those rules, determine whether that equality holds or not. Is that correct?
I mean, so I should be clear here. This subtlety only comes from higher order processes. So it's still the case that if I have two quantum channels and I take their tensor product, so that's like a normal first order process. If I take the tensor of two channels, this is again a channel on a bigger system. But if I have higher order things like process matrices or quantum combs or this kind of stuff, and I start taking tensor products of these things, you don't always get something you would expect. And the thing you get out is described by this logic. So the logic exactly captures what that thing is. Now, whether it captures that in a useful way depends kind of on how well that logical structure is understood, and that's something that we're still kind of working on and kind of understanding this logic better.
Okay, thank you.
Thank you. Pablo Arigi had written a question. I don't know, but Pablo, if you would like to say it out loud. If you're there, Pablo? He says in the chat he cannot. Okay, so I will read it for him. Just a second. Hello, the result is reminiscent of Weck's Abbott-Bransjard, showing that generic quantum control of quantum operations is only well defined if those appear linearly. Have you made the connection yet? I'm copying also the question in the chat so you can see it. Alex.
Yeah, I guess the short answer is no. I haven't really made that connection. I've been talking to John Barrett lately about quantum control in some sense. I've been thinking about kind of coherent control of processes. It's not clear yet what role that plays in this framework, but it definitely should. And I think the way that it will appear is that the way that it will appear is in the types. So things that are well defined should have types which match. So I should only be able to do an operation to some kind of process or higher order process if the type is right. It would be interesting to see if you could think about coherent versus decoherent control as something that you could get into the types in this kind of category.
Okay. Is there anybody else that would like to comment or ask a question?
It looks like there's a hand up still.
If I may ask a question, yes. Thanks, Alex. It's Alessandro Capurso speaking. Yes, thanks for your presentation. Actually, coming back to one of your slides in which you were basically presenting a situation that you define a paradox that was described basically as a loop. Can we conclude in this kind of description or formalism that whenever we have a loop, actually it's a kind of closed time-like curve that shouldn't have an orientation, because any orientation would be a possible paradox, while whenever we do not have a closed loop, we have some kind of possible definite order within relative definite order within the line of a single thread succession, while in parallel lines, if we do not have crossing lines between them, we might not know which could be the relative order among those two disconnected, let's say, chain of boxes. Can we conclude this from your formula? So basically that the loop identified undefined causal structure or paradoxical situation, while straight line are strictly causal sequence.
Yeah, so the consistent situations. Well, I mean, so one thing you can say is if I plug things together in an acyclic way, so in a way that doesn't create loops, then this is indeed always consistent.
Okay.
The converse seems to be a bit more subtle. So there are certain kinds of loops which are bad, and these are loops which can genuinely send information to the past, and these create paradoxes. But there are other things which somehow they formally look like loops, but the loop is broken somehow by a non-signaling kind of barrier.
So there is like a link that it's drawn, but in reality it's not there.
Yeah, it's like you have a somewhere along this loop there's a box, but actually this box is not really fully connected to itself. So if I think about if you have a non-signaling box, somehow that breaks the link from between the wires on the left and the wires on the right. So even though the picture is kind of connected, then there's a barrier there, a kind of signaling wall,
which is inside the box from what you're saying.
Inside the box, yeah.
Hidden in the box. So if let's say if we have explicit loop, this is a strong requirement for having an undefined causal structure, if we know what's inside the box, or at least we understand it's a connected link. While if it's linear, then we can define at least a relative causal structure. And coming back to the Bell's experiment from Marius, can we actually, and also connecting to the fact that we were mentioning before, like a kind of evolution of this system in time, basically, could it be like if that we have basically a closed loop which evolves as long as this part entangled pairs goes on Alice and Bob's side, and until the measurement is still basically an entangled loop, a closed loop. So kind of potential information that we don't know if it's there as a link or not.
Yeah, I'm not sure if you could. I mean, I think it does seem like this kind of framework has sort of good loops and bad loops, like the bad loops which cause inconsistencies, and the good loops which aren't really, you know, some kind of signaling to the past.
But also the bad loops, I won't say they might cause inconsistency. Maybe they cause inconsistency in terms of causal order, but still is a scenario that it's unmeetable, and maybe it's what it's explaining the Bell's pair experiment that Marius was mentioning before. Because as long as you have a closed loop up to a certain evolution time, let's say, you have still then determinant of in the causal structure, so the potential of this kind of correlation evolving.
Yeah, so I think there's maybe, well, at least two things you could mean by inconsistency. When I say inconsistency, I mean something like inconsistency with respect to measurement outcomes. So an inconsistency is if I have an agent and they perform a measurement, and the probabilities of each of those outcomes adds up to something different from one. That's a kind of inconsistency, which may or may not be related to the fact that, you know, these things have some kind of consistent causal order. I think having something which is never in a definite causal order, or at least never is until a measurement is made, I think that's allowed in this framework. There's nothing wrong with that. I'd have to think a little bit more about this kind of
We can take.
Okay, maybe we could move on to the next question by Paul.
Does the same logic apply to temporal orders?
How do you mean?
You could have like indefinite causal orders, but some people have argued you could have indefinite temporal orders for some things too.
I guess I'm not familiar with the concept of indefinite temporal order. What's the distinction?
A comes before B or B comes before A, and you can't really determine beforehand which it's going to be.
I think this is exactly what he's talking about when he says.
Okay.
Yeah. I mean, I guess the only difference is you've somehow abstracted a bit away from a temporal order where you have something like a fixed background time, and instead you're thinking about things influencing other things. So yeah, A having a causal influence on B that is kind of like A preceding B.
Okay.
Alex, I have a very silly question. is there any sense in which a physical constant could be encoded in a circuit? So could we have the speed of light and somehow say there is a finite speed of light? Is it already encoded? Maybe, I don't know.
That's a good and difficult question to answer.
Not well defined.
Yeah, I mean, I think I couldn't imagine you could encode the fact that the speed of light takes any particular value. I don't think these kinds of diagrams would see the difference in, you know, a universe where C is C and a universe where C is 2C or something.
But finite versus not finite.
I mean, the fact that you get diagrams and that these diagrams are sparse, and by sparse I mean the sense that not everything is connected to everything else, is capturing at least the fact that there are some events which are incapable of communicating with other events, even in principle.
Can you say again why? How does that? I mean, I'm not sure what sparse means. What is the?
So by sparse, I just mean that there are some places where there are not wires, right? So you could imagine, you know, that if I draw a diagram,
allowing there not to be wires. Yeah. Yeah, maybe that's good.
Yeah, you could say that the fact that there are any wires absent is capturing. I mean, you could say that it's capturing, you know, the finite speed of light, or that it's capturing any other kind of principle that you could use to you know, absolutely forbid communication between certain inputs and outputs.
Yes, I guess what's missing is somehow, you know, I mean, these diagrams are supposed to do what physics do, right? Does, in the sense of every time you want to analyze a situation, you have to make some approximation, cut an infinite amount of degrees of freedom out and keep few. And that's what, so I guess somehow the statement should be, if I let all the degrees of freedom that I neglected come in the diagram somehow, you still are never going to get some connections. Some connections are somehow fundamentally missing, and that's what would be having a space-like separation. Anyway, I don't want to insist on this because it's, yeah, I don't have very clear ideas on it. I'm just wondering if you know if these things have been cleared up or not in the literature. The connection with light construction in particular.
I mean, I think it's something that's sort of said informally much more often than it's very kind of rigorously cleared up.
Okay.
Yeah.
Ding, you raised your hand again.
Yes, I have perhaps so a question maybe related to Mario's topic, and it's about one of Alex's points in the final slide, in the concluding slide. You mentioned what's the big picture. One of the points is that you want to have the most general formalism to discuss causality and inference. I'm a bit concerned that things are not general enough because of the wires. Because the wires in your formalism, they represent causal propagation of, say, information or signal. But if you think like general frameworks, for example, we have Robert Wickel's general boundary formalism. There, we would have regions of space-time that are connected in space-like directions. We can have temporal boundaries that are composed with each other, and if we draw wires, they are, at least for infinitesimal region, they're space-like, and they wouldn't propagate information in a causal way, but there are wires there, and that there are correlations that are mediated. This we can see clearly if we deal with, say, quantum field theory. We have entanglements mediated by virtual particles. Is that a concern for you, that there is something more general out there that's not captured by the current formalism you use?
Whether I think there's something more general, I guess I would say yes. Whether I'm concerned about it, I don't know if I'm if I'm that concerned. Yeah, I take your point, and maybe what this could be a more qualified statement. It's something like trying to get the most general discrete notion of causal inference, where you're really thinking about discrete sets of events or agents, and building a framework around that. I guess you could imagine a version of this where everything is these regions, and I mean the thing that's kind of interesting about regions is transitivity fails, right? So I could have, for instance, a point in this region could signal to a point in that region, and a point in that region could signal to a point in a third region. That doesn't necessarily mean that original point could signal to the third region anymore. And the diagrams don't really see this, but maybe they could if you sort of started fine graining. So maybe I've got kind of coarse grained boxes, and I sort of start looking inside and inside and inside. I don't know. I think it's a good point. That this is the goal here, is to do something that's kind of as general as possible, but within these kinds of simplifying assumptions that everything is discrete, that we have these kinds of wires that are separated from each other rather than they kind of blur into each other somehow.
I guess even at the discrete level, we can have something more general, especially when we consider your other point in the slide about space-time.
Dink?
Yeah.
I'm not sure if Alex is familiar with what you're saying. So I completely agree with you that Robert is a much more general thing, because he's thinking about quantum gravity, right? But I think, so your point, what Dink was saying, is that when you have these wires, they're essentially saying time-lag separation. This box and the other box that are being connected have to be time-lag separated. End of story. There couldn't be an influence. And if all you have is these wires, then there are somehow other type of correlations that you could consider that live on the boundary of a region, which can have space-like parts in it or space-like corners. That's the kind of things you have in mind, I think, right? Personally, I don't understand. Is Robert claiming that he has a quantum circuit paradigm all developed that treats this case or not? I'm not sure what he's stating with the positive formalism.
I guess I read his long review paper, and he discussed these graphs. Like he has a manifold formalism and he has an abstract formalism, and you have these graphs connected by wires, and you have a positive formalism, and I think there the wires don't have to be time-like, so it seems it's more general already there.
Yeah.
So I think I missed the context here. Whose work is this?
I read it in the chat. Let me give you the background. This might be interesting for you, Alex. So Robert Eckel is now professor in mathematics in Mexico, in UNAM. He started with a PhD in Marseille. When he was in Marseille, he was in another group, but he met Carlos' group. He saw what was going on with quantum gravity, and then he developed a formalism that was adapted to spin forms, to a path integral formulation. The issue there is the following, basically, that you cannot think I go from one time to another. You have to think I have a space-time and I somehow take a region, and the quantum gravity effects are going to be in that region. So if you think of space-time like time plus space-time, so space-time, and I take a region, it's a very simple thing to do. Take any space-time, take any region that is closed, it has to have space-time, space-like boundaries. The best you can do is have two time-like surfaces, but then they have corners, and on these corners you have some angles that are gonna have to be between two time-like things. They have to go through a space-like path, and there is a whole story there. And somehow the whole subtlety of doing quantum gravity, at least in the covariant formalisms, comes down to that. What do you do when you don't want to think infinite time? Something happens infinite time. You really want to see look at the region of space-time. Then you cannot think in this way anymore. You need something more general, and he has this more general diagrams where somehow preparation and measurement are in the same box. But I'm not the suitable person to explain more. I think it could be interesting though, because he's doing this to as a sort of mathematical basis for quantum gravity, and already what he had, the previous thing, what was it called, boundary formalism, is a mathematical basis of spin forms. Then he wrote down this positive formalism in order to make a connection between the work like you're doing, and Bob Cook and Giulio and Lucian Hardy and Czeslaw Bruckner, hoping to link all this with quantum gravity. But I think this has remained, it was one of the things we wanted to do with QISS, but we were going to make meetings and have all you people meet, but it didn't happen. So I'm letting you know instead. It's going to happen sometime in the future.
Yeah, that sounds like an interesting thing to think about. So I mean, it could be that these corner cases, sorry about the pun, could be captured in these logics somehow. So you have different kind of connectives. Like you have I talked about this tensor and this par, and these are kind of like the signaling and the non-signaling connectives. But you have things that kind of lie in between there. So I mean, maybe there's something to that, and maybe I'm just talking nonsense. But yeah, I think it's something that I'd like to look at.
Is there any other? Lucian. Oh.
Hi. Yeah. So when I wrote this I had this causaloid approach to indefinite causal structure sort of about 15 years ago, and it was in some ways it was a general probabilistic operational framework, but it was more general in the sense that it wasn't a circuit-based framework. Although you could model circuit frameworks within it. I mean, actually one can think of it as a kind of hypergraph type situation where rather than having wires, you maybe have, you have sort of hypergraph links and so on, which take in 3 nodes or 4 nodes or so on. It seems like that's also a more general framework that one could look at these kinds of questions in. No, it seems to me that so one approach to the result that you quoted by the Jia Sakawada, that's Ding and Natika, 2 of my students. One approach, one attitude you could take to their result is that this shows that the process framework kind of fails. And then what you've done is to sort of try and actually recover it so you can have an internal logic and have a way of forming consistent statements. But in some ways, it would be better just to take the attitude that it's failed and try to find a different approach where you can take any composed diagram that you can draw down is an allowed diagram. That would somehow be a more satisfactory approach, it seems to me. And so it might be worth seeking in these more general approaches, so the stuff that of Urkel, the stuff I've done, and other approaches. Maybe there's a sort of maybe there's a more maybe there's a way of formulating things so that any allowed diagram, in fact, is consistent, or any allowed diagram is something that you can consider in your physics. Do you think that sort of project would always fail, or do you think there's some hope for that?
Well, I should say that I mean I guess my point of looking at this example of the tensor product of the process I don't see it so much as a failure. It's just that the tensor product is a thing. It's a perfectly reasonable thing that you can consider. It's just it's not a process matrix anymore. It's a different kind of thing. And the way that this more sophisticated logic kind of saves it is it tells you what that thing is. Okay, so it tells you it's now this kind of compound structure which allows, say, Alice and Bob, they can do joint channels, in fact, as long as their two joint channels they do signal in the same direction. So as long as they don't use this thing to make a time loop, they can perfectly consistently use these two things together. But this is something that's more elaborate than a process matrix, right? So if you write down exactly what this thing is, it's more complicated than a process matrix. But if you write down the type of this thing using this logic, that tells you exactly what kind of thing this is. I think you're muted still.
I took the liberty of muting you because we could hear the kids. You have to unmute.
Oh, right. Yeah.
Sorry. Sorry, the children in the background. Yeah, the dog may bark as well. But it's still the case, and I think this has been discussed already in this discussion section, that that you're saying you allow this thing as long as you don't use it in the wrong way. There's a box that you allow to exist in the physical world as long as you don't do the wrong thing with it. And that just seems like a strange sort of physics.
Yeah, well, I mean, I think it's a strange sort of ontology for having two process matrices, right? I don't really think we should think of these things as Alice and Bob are sharing two copies of a resource anymore, because then we really think about, okay, well, now we have to put this restriction on Alice and Bob that they don't do the wrong thing with this resource that they share. I think that's the wrong way to think about two of these things together. But I don't know what the right way is to think about them. Yeah, I don't know what the conclusion is to that. It is. I think the failure there is not necessarily with the formalism, but with how you're interpreting its kind of pieces and different kinds of compositions as things that could in principle happen to some agents out there in the world.
Lucian, if you're saying something, you are muted.
No, I was just saying thank you. I think it needs more thought about this. I mean, personally, I would prefer a physics where every allowed object. I mean, just in Newtonian physics, or if you have a rock, then it's always a rock. A rock is a rock. You can use a rock in a different way. you know, in quantum information, like, you know, as presented in Nielsen and Jung, any box you have is fine. You can use it, and yet suddenly you get to it. It seems then suddenly something different happens. And whilst now your approach shows that you can treat it consistently, it just seems weird.
I mean, you know, even with quantum circuits, there are some rules, right? I can't just take an output to a quantum circuit and just plug it into some input, right? That's something I'm not allowed to do. But we think that's a very natural thing that I'm not allowed to do because that makes sense with the operational interpretation for what a circuit means. Happening in time. And now what does it mean to take a qubit and actually plug it into something that's already happened? It's just very difficult to give these higher order things interpretation.
Are you saying you can't, like, I mean, an example of something you can't do, or typically don't do, is mismatched types. So you don't send an electron into a input associated with a photon. Although you can do that, it's just then your characterization of those objects fails. I mean, you can send, you can throw rocks at a beam splitter if you want.
Yeah.
But then the way you characterize those objects simply breaks down the mathematics you have associated with them, doesn't suffice to give you predictions.
You haven't looked at the subspace of that operator, which handles the rock as the input, so, or something.
But now the example you have now with the with this result of Ding and Nitika and also the Vienna group, it doesn't seem like it's that type of result. It seems it's not just that you're not in the right subspace. It seems that sometimes you can do this and sometimes you can't, and so you need a more sophisticated logic. But it doesn't seem like it. I could imagine expanding my logic for throwing rocks at beam splitters. I would just have to have a more sophisticated mathematics, and then I could describe that as well. You know, the output being some broken glass or something. But I don't see that I can expand. In this case, it doesn't seem like it's the same kind of thing.
Well, no, I mean, so I think a more analogous example than the rock and the beam splitter is just thinking about doing something with a quantum circuit which causally is not meaningful, right? So taking an output of my circuit and just plugging it back into an input, right? So putting you know, a time-like curve or something, which, I mean, you know, that may or may not be meaningful. In the usual circuit model, this is not a meaningful operation, right? Because the result is not a unitary circuit anymore. It doesn't describe an evolution of your quantum state. I think I'd like to think that these higher order constraints are things like that, right? So it's not meaningful to take two process matrices and put them side by side and expect to have a process matrix again. So that's just not something which causally makes sense. Now there could be some kind of, you know, physical situation that agents could get themselves into, which does correspond to the tensor product of two process matrices. But the only thing that's meaningful to do in that universe is that Alice and Bob both send information in the same direction.
Okay, thanks. That's helpful. I think the example of a closed loop just in standard quantum theory is a good example. It's something you can draw, but it's not allowed. So I think it's not like the throwing rocks at a beam splitter example. Okay, I'll think about this more.
All right. Great, thank you. There is one hand up. I'm not sure, Leah, if you have another question. And Konstantinos is commenting something about this paper. I really don't know. I have to look into it. I don't know if Aleks as an answer to that.
I wanted to ask what is wrong with if you try the naive approach of encoding the speed of light in a diagrammatic calculus, so imposing a light cone, so having wires only be allowed to be time-like, so within the having some slant that is within the light cone time part rather than the space-like part. At the very least, that would so having horizontal distance represent space separation and vertical distance represent some metric, Minkowski metric on time. At the very least, that could answer the question of whether information is propagating faster than the speed of light. But I don't see how that would interact with the rest of causal structure.
Yeah, I mean, I think this is something you could do. This would involve putting, I think, some more structure on the diagrams. So you could associate, for instance, boxes with points in Minkowski space, and just say, you know, subject to the condition that there's not going to be wires. There can't be wires connecting space-like separated points. In a way, you could see the diagram as a kind of abstraction away from that space. So just to the causal structure. I mean, so it's like, you know, even more abstract than just taking the conformal structure. We're really just taking some kind of discrete causal structure of some points. I don't think anything particularly would go wrong if you do this. And it seems like an obvious thing to do that maybe someone has done, but I'm not aware of any work that has really, you know, done that in a fully rigorous kind of way. It might be an interesting thing to look at.
Sorry, can I add something here? I mean, given a circuit which is a bunch of boxes connected, outputs connecting to inputs, I think you automatically get a light cone.
Yeah, I mean, you can sort of take the kind of upsets and downsets of, you know, all the things that are connected transitively.
Yeah, I mean, if you're trying to do tensor network calculations for big circuits, I mean, you actually use this thing to only compute the things inside the light cone, and that's how you also do slicing for big tensor networks to distribute the computation on independent GPUs, for example, right? I mean, there is structure in there from the moment you have things connected and someone gives them to you. It's what Mario said before, like the wires give you a lot of structure already from the way they are connected, right?
What I don't, I mean, maybe I don't know, maybe something silly. What I don't see is how you differentiate. So again, these circuits can describe many situations. So you can place yourself in a Newtonian setting. So quantum mechanics, which are what these circuits are mainly doing. It's non-relativistic, right? And I can just say there's two things that are, you know, they're not interacting. So I would hesitate to say just look at that diagram and you deduce a light construction. I mean, maybe you're actually assuming Newtonian spacetime, and that's fine. So I don't know. I just want to sit down and see if there is anything really encoded that you can encode. If it might be that these circuits are simply general enough that they can describe Minkowski spacetime or not, or there is something interesting, but I don't know what that could be.
Yeah, I mean, it's almost an interpretational question more than anything else. You know, how I'm going to interpret these diagrams. Do I interpret the absence of a wire as a space-like separation, or do I just interpret it as, you know, here's some devices on my table, and the absence of a wire means those devices aren't plugged into each other.
Yes, exactly. So these diagrams don't come with an ontology out of the box. They really depend. it really depends on what you're trying to do with them, right? If you're trying to do quantum gravity, maybe also it doesn't matter if you're a realist or if you just think about the data and measurements and you're that sort of person. You can still use them to do quantum gravity, right? And that's how Einstein even started GR, thinking what happens, what you would observe if you move fast and stuff like that. So then discarding, for example, would mean you don't have access to the information because the universe doesn't let you, like it's in a black hole or something. Also, side note, there's some work where the black hole entropy and the area law and things like that, it has been tried, to rederive the entropy and the scaling of the entropy of the area just in terms of discarding a bunch of degrees of freedom inside an area in space-time. And then you say, oh, look, if I'm not allowed to look, then I get an entropy, a von Neumann entropy, which scales as the black holes one. So the discarding means I literally cannot access the information. Now, if it's a device on your table,
That's
right?
because of light's construction in that case.
Yes, exactly. Now, if it's a device on your table and you're measuring some qubits or you're doing something with photons, I mean, in principle, you could measure. Like you gather all the data and then you just do a partial trace. You can sum over a bunch of configurations available to a system, and that's discarding. Or you could have not measured at all, and that's equivalent, right, mathematically, because the universe does the sum for you, basically. I mean, it's cheaper to just not look rather than look and then sum over all possible samples.
Yes, I'm wondering if discarding could be, I take a system and I take it at space-like separation. And so you lose access to it. It's like what you're saying. It's not the same. A black hole is different.
Black hole is different because you have no choice.
Yeah, because you're time-like separated. It's just that ingoing and outgoing are going in the same direction.
If it's on your table, you're simulating having a black hole, say, or something like that, like a baby one on your table.
Yeah, I guess the question is, given a certain framework like Alex's, what can it describe? And what it cannot? What, for instance, like Ding was saying, if you want to do covariant path integrals in quantum gravity, probably you cannot represent them in this way.
Yeah,
it would be interesting though somebody to sit down and say, okay, look, Minkowski physics, I don't know, non-relativistic quantum mechanics. Okay, check. Relativistic quantum mechanics, yes, we can do that too. In the discrete, fine. And then see somehow where things get stuck before you reach quantum gravity. What is the quantum field theory on relativistic on curved space-times? Is that okay so long as we stay with finite degrees of freedom? I don't know. I'm not sure.
Can I add a brief comment? So maybe it's interesting also to check quantum theory on the classical relativistic spacetime, even in the discrete case. Maybe we can check lattice field theory. I'm not actually sure in this framework we can do that because there we do have space-like wires. That's something that's not in Aleks framework.
So for sure, there's people simulating lattice gauge theories with tensor networks, which are basically these string diagrams where you interpret them over some specific vector spaces or group representations if you're doing non-abelian stuff like chromodynamics. I'm not an expert on this. I haven't read these papers. I just know it's a thing people do. And there are attempts to do QFT in the second quantization with these tensor networks, which are again are diagrams, but I think it gets hairy. Also, there is Stefano, right, from Oxford, who has looked into formalizing QFT in this diagrammatic categorical approach, but I don't know how this fits into all of this. The other question I had was for higher order processes, like Basically, so at the first order, where taking a tensor of two maps, say, gives you another map, so you don't have a problem. You don't need this new symbol.
Mhm.
What does this logic of causation buy you? Or to ask it differently, when do I need to consider higher order processes? Like second order, for example. So at the end you proposed, let's do quantum gravity, and you have a lot of pictures and all of the boxes are cones. Was there any reason for that, or was that artistic?
I mean, that in that picture, I guess the rough idea I was trying to give there is that the boxes are not combs. They're indefinite. They're indefinite things.
They're indefinite things, and the idea was that you will coarse grain to get definite.
Yeah. So your logic buys you the laws of composition of, say, little pieces of indefinite causal structure. And maybe something that kind of emerges at a large scale is indeed some kind of light cone structure or something. So you could maybe see a passage from indefinite to definite through composition or through coarse graining.
Right, and the logic,
this kind of thing. Yeah.
And the logic enforces constraints so that after you coarse grain, you get something definite.
Yeah.
Okay, that actually clarifies something. Okay, that's nice. So finding these proofs for this logic with that old program, it's efficient, right? As far as I understood.
It depends somewhat on the logic. So checking the proofs is almost always efficient. And it's typically it's easy to find a quadratic algorithm for doing this. And then people think and eventually come up with linear time algorithms for doing this. So in fact, this one that I cited is only from like 2 years ago or something. They came up with a linear time algorithm for checking MLL plus mix. But the proof search problem is harder. But if you think about this kind of operationally, proof checking is basically, I have these two processes and I plug them together somehow. Now, does this make sense? That's proof checking. That's really, I'm hooking the wires together in a particular way and I'm asking you, does this make sense? The proof search is saying, is there a way I can plug these wires together that makes sense? Okay, so maybe they're all qubit wires, and now the reason that this goes exponential is I have to try all the different combinations of ways I could plug this thing together and then check it. And that's I think for MLL it's NP complete, something like that. So it's
okay, so it is hard. Okay.
But in the grand scheme of things, not that hard. As hard as other hard stuff that's not that hard. Let's say.
Yeah, well.
as hard as sound, but it's certainly not, say, undecidable or something like this. So.
Yeah. Okay.
All right. So we are at 2 hours and 10 minutes. Usually we stop about now, except if there is somebody that would like to say something. I can give you one last opportunity.
Maybe just to mention something here on the discussion. I first wanted to mention also in relation to previous discussion about these more general theories that were suggested here. it is about this theory that was discussed earlier about this, where we ignore the forbidden events, but we essentially allow all kinds of things to get together in this time symmetric or time neutral version. So there exists this kind of circuit, if you like, language, but it has no directions and includes all these time-like connections, a la Robert Oeckel, that we formulated some time ago. But there, and so essentially there everything is allowed, as Lucian said, with the exception that there are some things that actually are not allowed. And so there are some impossible things, like, as you said, if you have a closed time-like curve, you cannot just put the NOT gate there. That kind of combination of processes is not allowed. But other than that, there is this version of process matrices, etc., etc. You can put them all together, you get valid processes. But the whole interpretation is different. And I think this is very essential here, is about the interpretation of these objects and the interpretation of these diagrams. And so I think that the theory, as Aleks described it, makes complete sense for the type of interpretation that it is meant to have. And there is a certain time asymmetry here. This is this discarding effect that we talked about, what it means in practice and so forth. I think what is essential here is that something that Aleks mentioned is the word deterministic processes or deterministic objects, right? This property of causality holds for supposedly deterministic transformations. And in my view, an essential, something implicit that we all have in mind when we speak about deterministic processes or deterministic instruments and so forth, is that these are things that we realized without using post-selection. So there are things that we can set up and do them, and they happen 100% probability. But of course, if you perform some measurement and you get a measurement outcome, after you know that you got it, I mean, it occurred with 100% probability. It's provided that it's just that this knowledge you have it later in time. So that is to say that here, I think this theory makes sense for assuming that we are in this universe in which certain rule holds for pre-selected processes, and we can build up all this structure about how we can compose different indefinite causal structures and what makes sense and what does not make sense. And I think this is all well defined. And there is another approach, the one of Robert Oeckel and variations that we have developed, including the discrete circuits that we've developed. And these two, I mean, there they have, I think, the desideratum that Lucian mentioned, that we can combine everything, but there is no hierarchy. All the processes are just of the same kind, because you can compose everything with everything, and the whole higher order hierarchy for processes just doesn't exist. But it has a different interpretation. That's my point. For this theory to make sense, you have to think about what these boxes represent. And so in particular probabilities, I mean, if you just compose the linear maps, and you get some numbers, these numbers are not the probabilities in such a theory. So if you have various outcomes and you have a given box to get collection of possible events that could occur, outcomes of some measurement, then if you consider a whole circuit of this, the probability, I mean, the numbers that you will get by just composing these linear transformations essentially are not probabilities, but you have to sum them and you have to renormalize them by the sum of all of the possibilities, and this gives you probabilities. So as to say that I think these are different things and they both make sense. And I personally would be also very intrigued to see how this category language could actually, what it has to say about this other type of theory, which doesn't distinguish time, but is more time agnostic.
So is it at least clear what is the operational interpretations of your boxes and your circuit?
The operational interpretations, is this a question to me?
Yes.
Yeah, the way this is interpreted there is that a box is normally, this is phrased in the language of instruments. Essentially, you have a set of possible events, or sometimes you may have just one event in a box, which is, you may regard it as deterministic. But all of that is knowledge. It's about someone's knowledge about the set of possible events that can occur in a given region. And that knowledge might be available a posteriori in time, in practice, or might be available a priori. And there might be different reasons why certain things you may know about or may not know about in advance. But you are free to learn about it and update your description of a box, and therefore just consistently talk about what we normally call post-selected type of operations, that they're just as valid because their interpretation is knowledge.
Right, thank you. So I think we should give a chance now to Alex to maybe summarize his talk, say whatever you want, and then we wrap it up.
Okay. Well, I don't have anything in summary to say, but actually what Ogden was saying gave me a hell of a lot more ideas of things to talk about, but I don't think I can say them in 2 minutes to wrap us up. But yeah, maybe I should just say thanks for inviting me here, and thanks for the discussions, and hope to see you all again soon.
Thank you, everybody.
Thank you.
I'm gonna stop the recording and the YouTube. Yes, clap. If you want to continue chatting, feel free to use the Zoom.